So as promised, I wanted to talk you through. Actually, could you close the door? I don't know why, but I wanted to walk you through what I learned at Pantex in terms of setting up teams to solve problems. And so, in order to solve problems as a team, you've got to also know how to solve problems individually. Okay, and it was a part of this program that was a Six Sigma training. And they gave us these little books. This is a black belt memory jogger. So you had different levels of training in statistics and process improvement. And for sort of the just general office person or whatever, they would send them to green belt training, where they would cover things like, this is a pie chart and it goes to 100% and the wedges represent amount, and relative amounts can easily be seen with a pie chart. And then the yellow belts were people that would maybe make a pie chart. And then the black belts would be people who understood statistics and did design of experiments and managed teams to solve problems. And it was a fantastic experience. The Six Sigma thing, sigma is traditionally the uncertainty in a normal distribution. It's the distance from the middle to the inflection point on that normal distribution. And so it's a measure of uncertainty. And that's what we've used in science, in statistics this whole time, is sigma to represent the uncertainty in a population, meaning a large number of data points. Well, the idea of Six Sigma is you want your uncertainty, the mean of your process and its width, you figure out what your uncertainty is in that, and you want to have at least 6 uncertainties to your nearest customer specification. And so you think of this, I teach this in forensic chemistry, where if you have, this amount here in a drug test is going to be classified as a controlled substance, in terms of a concentration, you want your process to be able to measure things below that, so that if the uncertainty in your process, ideally, would be 6 sigmas away from the line, we're going to put somebody in jail. Right? That's your customer specification to say, okay, this is a controlled substance, cocaine or what have you. And if you get a low value, you want to have confidence that it's a true result and that it's not going to accidentally put an innocent person in trouble. And likewise, if you're on the positive side, you don't want to let a guilty person go away just because your instrument's noisy, right? And so this could also be translated into any kind of quality process, to where your uncertainty is narrow enough so that you're 6 sigmas away from a mistake, basically. We typically use, for limits of detection, 3 sigmas. So if you do a blank, and this is something that's valid for all of your work, if you've got an instrument or a measurement and you want to know what your limit of detection is, a good rule of thumb that people use is 3 sigmas. So you measure your blanks and you measure them multiple times and you figure out what that uncertainty is, that signal. And you take that uncertainty and you multiply it 3 times and add it to your average signal. And you can't confidently say you've detected anything if it's below that value. So your baseline measurement value plus 3 times the uncertainty of that value. So 3 times that value would be your detection, limit of detection. But what if you wanted to quantify it? How sure would you be? You wouldn't be very sure at only 3 times your baseline level. And so another rule of thumb would be 10 times that baseline level. Then you could be confident that you were able to give it a number, milligrams per liter. You could quantify that if it was 10 times your blank value. So those are some statistical measures that we use. But let's talk now, that's the Six Sigma program in process improvement and control. And as a part of that training, they taught us in this method called the DMAIC model. DMAIC. And so in any process improvement, let me try to find a darker marker. Video very well. You're going to go through these 5 steps even if it's just a small problem and you're trying to figure out what happened, okay, or what to do next. You bump into an error in your Gaussian calculation and you say, okay, what do I do next? This will still help you, even though it's not some grandiose process improvement project. It's just how to figure out what to do next. And so these are the 5 steps. The first one, D, is define. M is measure. A is analyze. I is improve. And C is control. So these are the mental steps that you'll go through anytime you run into a problem. Because if you can't define what the problem is, then what are you supposed to do? You know, how do you go and find a result? How do you, if you can't get your hand around measuring the problem, you know, what indicates that you have a problem? That's probably some sort of measurement. And then analyzing that, is it random? Is it always depend upon this event happening? You know, and analysis may involve doing some trial and error and seeing how the process is behaving. And then improving is actually putting a plan in place to fix this problem, figuring it out, maybe changing your method. And then control is not just controlling it so it doesn't happen again, but documenting what you did and the thought processes that you went through. And so I definitely want you to understand these 5 steps. And so we'll talk about each one individually. And I'll try to apply it to some of the problems that you're going to run across, like calculations that die or results that are difficult to interpret. And so I'll definitely, in that point, want your feedback if you've already run into some troubles. And then I can apply it to that problem that I talked about with the temperature measurement using the rotational lines for carbon monoxide. You know, so that we've got a problem there. Let's see if we can define what the problem is. Let's see what kind of measurements we have, what kind of analysis that would, you know, provide a different approach to that problem. And then if we were to implement that, what do we think would happen? Okay. So let's focus on the define step. The most important question that I have whenever I'm in this define step, and a lot of times people say, let's make this better, like a campus committee. Let's make this better. And my first question is always in this define area, and it is, where or what is the pain? Where is the pain? There's got to be some pain or that you're trying to fix. And if you can't define the pain, good luck trying to find a fix. Right? If this isn't a problem, let's quit now and go get coffee. Right? But if you're in a committee meeting that's just spinning its wheels, this is the question to ask. What are we trying to fix? If you can't define it, you can't fix it. And so let's think about that temperature problem. We had the rotational lines for carbon monoxide. And they looked something like this. And we had a great formula. We did some calculus. It was nice to flex those muscles. And we had the derivative of that curve, the probability of the maximum J value, you know, as it depended upon temperature. It was beautiful. Okay, we could find the max J value and tell the temperature. But what was the pain?
Too discrete.
Too discrete. What do you mean by discrete?
There might be a maximum that we can't discern immediately from looking at the data. So
like this one?
Yeah.
Yeah. Like, is it that one or that one?
Or between.
Or between. Yeah. So it's either this one or that one. I think that's what you mean by discrete. Yeah. What else? Did anybody else identify? So let's go write these things down. So our temperature model. And you may have to, you know, spend some other sentences defining that term if you're working with other groups. Okay. What other pains did people see that maybe a different way to say this or different, just a different identity of what might be the pain with our temperature model?
I'm trying to figure out how to put it into words.
And that's what this exercise is about. The define part is how to put it into words.
It was also done like a large range of possibilities if you base it off of this one or this one.
Okay, so if it was J equals 6, it was one temperature, J equals 7.
It was this other one, it could fall anywhere between that.
So that, in terms of our term, like let's use our, just broadly scientific vocabulary, what would we call this range? Like if you picked J equals 6, you had one value, but if you picked J equals 7, you had another value. That was so, I'm going to pull on her. So this was a good one. No, that's okay. You got this big range. What word would you put on that range?
Other than range?
Yeah. I mean, to me, when I think of range, I've got, this full range of data. You're trying to figure out the temperature. If I analyze it one way, I get, say, 200 Kelvin. I pick a different peak, I get 400 Kelvin.
So like X gives you Y type thing?
Yeah. I'm thinking accuracy or precision. Which would that be? Precision? Why is that? Because if you have uncertainty in J, you have uncertainty in T. And what do you think your uncertainty in J is? We were saying 6 and 7, but that was pretty much it. So let's look at this. We've got a choice between J equals 3 and J equals 4. Okay. So I change J by one value, and my temperature changes by a couple of hundred. So yeah, that's precision. It's not a very precise method. So the precision is awful. So now that's a very specific statement, that this model has very bad precision. So that's a great definition. So we've identified where a huge pain is. Now I think this might be more related to a cause, okay, than a pain. Because discrete data is not necessarily bad, but bad precision is bad. Yeah, so I like this as a pain statement because it's saying we have discrete data, and if I pick a different discrete J value, I get a huge change in answer. What about accuracy? This was a room temperature sample. I had the spectrum up here, it was room temperature. So, tell me about accuracy. Someone over here, you four, my team on the right. So let me tell you the data that we just came up with. So I said if J, so we go and measure a little bit. If J equals 6, Jmax, T was, what did I say, 200, okay? If Jmax equals 7, T was, I'll say 350. I think it was something like that. Okay. I said at 400 already, but I think actually what we were looking at in our model was 350 or something like that. So tell me how, if this addresses accuracy at all. Does this address accuracy? Or is accuracy in this result at all? This is definitely a precision problem, but is it also an accuracy problem? You can't do accuracy without a true value.
But can't you say the true value would be 1 time?
Yes, so T true is equal to 298 Kelvin.
But if that's an unknown, you can't bring accuracy.
But I'm telling you, this was a room temperature sample. So yeah, we'll say that T true is 298. Do you follow that now? So you as a team here, give me a definition of our pain related to accuracy. Go ahead. No? Yes.
J value is comparable to the observed value that we have. J value, reference J value is observed. Is it related to the observed J values that we
Yeah, so if we have the spectrum, that room temperature, and we find the Jmax, and they're really close, which one's maximum? Is it just because of noise that 6 is high? You know, if they're very equal, you might say, well, it might be 6, it might be 7. And so if we said, okay, what if it's 6? What's our temperature? 200 Kelvin. What if it's 7? You know, because we can't really tell. It might be 6, it might be 7. So let's say, what if it's 7? 350 Kelvin. So this is a problem with our system, our way of measuring temperature, because precision is very bad. Can you give me another phrase about accuracy? This is the data. We're trying to define our pain. We're analyzing the system. So a lot of times these steps go hand in hand. When you're defining, you're also measuring and analyzing. But you're sort of oscillating between those three things. So I just want a phrase, like one of these phrases, that addresses accuracy. Y'all can talk amongst yourselves if you wish. Tashina, you can scoot over there and talk. Okay, let's come back together. Y'all are waiting me out. I know what you're doing. You're like, well, if we don't say anything, he will come on and give us the answer. But it doesn't have to be initially that complicated. So you could just say accuracy is very bad. Okay. Yes, accuracy is also bad. Now, let's get a little bit more detailed and say why or how do we know? Right? If you tell me precision is bad and I'm your manager, I'm going to say, okay, of course, everybody could be more precise. How do you know precision is bad? Right? Because delta J is plus or minus 1. Plus or minus 1. And delta T is plus or minus 150, so plus or minus 75.
This would fall under measure?
Yes, measure and analysis, but we're defining the pain, and then we're looking at the data. So you really have this historical data to look at. You've done something, and you feel pain, and you didn't define the pain.
Why do you cut that in half?
Plus or minus. I wanted to do plus or minus.
Wouldn't it be plus or minus 0.1, 0.5?
Okay, yeah, you can do that.
Sorry.
Even worse, right?
Yeah.
Plus or minus 0.5. And then huge, so 75, yeah. So I'm just trying to find out a specific way to define precision, right? If I pick a different J value, then boom, I've got a huge change in temperature. Now accuracy is very bad because I could either be high, pi by like 52 or Kelvin or low by 98. Right? So that's the problem, isn't it? So now we're not just, this is good. At first we have a general definition of the pain. Precision is bad. Then we get more specific. That's great. This tells you, you know, some numbers, and you can talk to people and say, yeah, our precision is so bad. We have a 75-degree swing, depending upon, you know, plus or minus a J value, or we're either high by 52 Kelvin or low by 98. And that's a real problem for accuracy. So this is a very good set of definitions. Now, like I said, this I think is a clue as to the way to go about solving this. Okay, so the discreteness of the values, right? You get this result or that result. There's really no smoothness to it. So you have discrete answers for every one of these J values that you pick. And so that's a clue for what to attack. And so when we get to the analyze part, we're also analyzing a path forward. And then implement is coming up with a plan to address the pain. So let me focus on a few of these things. So during the define statement, during the define portion of a deal, you have a problem statement. Okay, so these are some problem statements, and that sort of falls under where's the pain type idea. This is also where you define, if you're in a business, right, you're defining what the project scope is, what the project goals are. So if this is thinking about a big project, then this is the stage where you say, all right, we want to attack this problem. We're going to, you know, come up with a model that would apply to every temperature from 0 Kelvin to infinity. That's too big of a scope. Do we want to measure temperatures near around, you know, room temperature? Then we have to have a very precise model. If we want to tell the difference between 298 and 299, then, you know, we've really got a narrow scope in a very difficult project. So it can be too big and therefore too difficult. It can be trying to nail it down too precisely and be too difficult. So scoping your project is really important. And what y'all have been doing with your calculations and your Gaussian project has been a lot of scoping. How big is this project going to be? Am I going to do every possible Baroxy, I never can remember the names of these enormous things, you know, or there's not enough time for that. And so scoping the project is part of the D step, the define step. What are we actually going to do? Okay. And then also definition of performance measures. So in this case, our performance measures are going to be, you know, how precise and how accurate our temperature results are. We don't really have a goal set in mind for this temperature problem, but we would like it to be better than this. Okay, so we don't have a very, very specific target. You know, do we want to control temperature or have like a thermometer that has 10-degree increments or 5-degree increments? You know, what's our goal? That's where we would define that. Now let's go to the measure phase. So we've identified our inputs. Our input is the rotational spectrum of carbon monoxide. Okay, but one thing that we have been, the old project only focused on Jmax. And I think that's a problem, because we have a lot of other data. And I think this is the key that I wanted you to think about. When I said this is a problem I think you can solve, that's going to have to be creative. You're going to have to get away from what you were given. You were given Jmax, but you're also given a lot more data. And that's the mental creativity that you've got to have to solve problems. You've got to say, wait a second, I've got a lot more information here than just Jmax. And so in terms of this analyze and step, the measure step, you've got the data here, you've got measurements at you know, 20 or so J values. can you use them all instead of just the maximum? And you can, because you have that formula, P sub j. That P sub j formula tells you the intensity of every one of those peaks. And that P sub j formula is a function of temperature. So could I do this in Excel, where I have the intensity of my experiment, every one of those j values, and then in another column, the predicted intensity based upon temperature. And I fiddle with the temperature until I match all the intensities. And so how would I tell if this column matches this column? Take differences. Some differences are going to be negative, some differences are going to be positive. And so if I add them together, they're probably going to cancel each other out. So I'll probably square those differences, so they're all positive, and then add the squares. And that's a common thing. And if I take the square root to kind of get it back down on that, that's called the root mean square difference. Okay? The mean part I could divide by the number of data points. So the RMS value of this fit would be something that would tell me how close my temperature model fits all of the data, not just Jmax. But the thing I was hoping that you guys would do mentally was to recognize, hey, wait a minute, I don't just have Jmax. I've got all of those rotational lines that I can use. And I've got an equation that would fit them all. And so that's part of the measure phase, is to identify the inputs and the output. The output you want is temperature. That's what we're trying to find with that problem. This is measure phase is when you would do baselines. So controls. Now this applies to your Gaussian projects, right? You can't do something unknown until you've done something known. So you would come up with some known calculations, some of the ones in literature that have a method lined out, and so then you repeat that one from the literature, and then you feel comfortable with the method, and then you apply it to your unknown, the one that relates to your research. So that's the measure part.
I
Yes.
think this step, when considering the scope of the problem, the temperature, temperature problem, the measures, the identification of the measures seem a bit ambiguous, because I kept going over, well, am I going to have, or am I simply looking at the spectrum?
Yeah.
Or am I actually looking at the data?
Yeah, because you came and talked to me, and you were asking about the spacings between the lines and stuff like that.
Right.
And I was trying to steer you back to the temperature effect, because the spacing between the lines does not depend upon temperature.
Right.
But the maximum of each line, or the height of each rotational line, does depend upon temperature. Right. And so I was trying to steer you back to the because there's lots of inputs. The spacing in the lines is an input. You know, the full spectrum is an input. Even the baseline is an input. But which ones are the relevant? And that's what the measure part is. Let's define and measure what's the thing we're after.
So for me, I was trying to do it. So if somebody handed me a spectrum,
Mm-hmm.
I had no data other than the B value and the spectrum
Okay.
of what is handed to me. So I have no values of those, of what the
Right.
intensities are. How can I figure out an accurate temperature just based on the spectrum, not knowing that I would have access to the actual numbers of the intensities?
Okay. Yeah, if I got that, what the situation you're describing, okay, I would get a ruler out, and I would measure the intensities of those lines with a ruler.
I thought about that.
And that sounds dramatic. It's like, really? A ruler? Yes, I've had to do that. I've gotten data that was from an old journal article, and there's no table of numbers. What are you going to do? They have actual software that can digitize a spectrum. So you can turn in like a scanned spectrum, and this software will line follow and turn a spectrum into numbers. So you can take a graph out of the literature and get a data file. And because of this very problem, people have produced, say, chart recorded data. There are no numbers with a chart recorded data set. We used to have chart recorders. The voltage went up and the pin moved to the right, and then the voltage went down, the pin went back down to the left. And you had to digitize that sometimes if you wanted to use it in a spreadsheet. So yeah, I would figure out a way to peak pick that spectrum and get the maximum values, and then I would match those, whether it's inches or absorbance, they're all relative to each other. So
because my problem I kept running into, I was trying to solve for two unknowns.
Yeah.
With one equation.
Yeah,
And
that's
that's
right.
impossible.
So I think this deciding on controls is critical, and then figuring out what inputs you need to help you fix the problem. Okay, first of all, help you define the pain, and then what kind of inputs you can use to solve it. So we use the Jmax to define our pain, and then we have more inputs, the other J values, that we can use to come up with a different solution. So the analysis phase, again, these are not so clearly defined. Analysis is finding out what those critical performance values are. The measurement piece is sort of looking at the data that you have, and the analysis is analyzing it, but then also the analysis is kind of coming up with what you're going to do with that. So an analysis here, the measure part would be, say, recognizing our Jmax values, helping us to define the pain. The analysis piece would be, okay, we've got multiple J values, and we're going to now use them to come up with that model. And that would be the improved part. So during the analysis, we're looking for improvement opportunities. Going from discrete values of just Jmax, 6 or 7, to more values. It's still probably not as continuous as we'd like, but it's more continuous than just picking one of those J values. So moving towards continuous data is an improvement in this case. So let's erase these. So we had measure in there, analyze. Let's look at the improved part. So the DMA process, so that sort of cycling through define, measure, analyze, gave us some insight into the X and Y relationships. And in our case, it was J and T. So not just Jmax, but J and T, how these relate to each other. And it was that P sub J is equal to 2J plus 1 e to the minus E sub J. I'll go ahead and write it out. B times J times J plus 1. B times J plus 1 over KT. So a nonlinear relationship. We have the J values here and the temperature there. So it's not something that we can just, it's nonlinear. This is the shape of that curve. You've got the J values. And if we plot this function, it looks like that. And so this would be T true, a great fit. Too cold. And T hot. So we know those relationships because we know this equation. And in a spreadsheet or some other tool, you could even write a program for it if you were in industry and you wanted to just track this. You could look at these residuals. Take these differences between your experimental and your theoretical and square them, add them together. So the sum of the squares of y I minus y, let's see,
Y co-loader lecture.
yeah, I'm trying to think of, I'll say theory, TH for theory versus experimental EX, okay? Squared. So we take those differences, we square them, we add them together. If you wanted to divide by the number of points and then take the square root, you get the RMS value for the match between the theoretical and the experimental. What happens when these go to be the same value? This goes to 0, okay? And so your RMS value will go to 0 if you had a perfect fit. And so you can use Excel. There's a tool called Solver. And you can change T and let Solver fiddle around with T and make RMS go to 0. And then once it's done, Solver will have told you the best temperature to fit all of the data. So that's a great method for solving this. So that's sort of this implementation, is to come up with this plan. We're going to use the RMS differences between our theoretical and our data. We're going to let Solver guess the temperature until they match. And Solver actually does some Newton minimization, like it changes temperature, looks at the slope, and then runs down to the best fit. Kind of like what Gaussian's doing with the molecules. And so this would be a great implementation, and then you implement it and see if it works, and see how good the problem works. Now and then control. What is control? Well, if this is a company and a process, you don't want to finish the project and walk away. How are we going to continue this process? Now, what is our control? We don't really have processes to control, but your research groups do. You're going to write your master's thesis and graduate with great fanfare and leave. And we're going to cheer you on, okay? But all the good stuff that you did better be written down somewhere. Not everything is going to go into your thesis, surprisingly. You're going to have experiments that don't work. You're going to have side experiments that you thought might be fruitful, and they're going to be dead ends. You're not going to include everything. You really should just tell the story of your research, not chronologically, but this is an interesting set of molecules. We synthesized it, we had a few problems, but these are the results, and here's the conclusion. You pick a subset of your research that you put into your thesis. It kind of sets up, here's where we wanted to move the ball, okay? And we did this research, and we moved it. Here's our conclusions. There may be a lot of other things that you did that just are not in there. We don't want to lose those things. So the C part of control is documentation. Even if it's not especially, I would say, especially when it's not documented in your thesis, you need to get it written down in your notebook. You need to have PowerPoints and things that you've done for group meeting. You need to annotate those. If you have things that apply but probably aren't going to go in your thesis, you need to write out in the little notes view of that PowerPoint, or if you have notes that you've prepared in a Word file or whatever, make sure that it's obvious to students who come after you and your advisor that those things are together. These are the notes for this PowerPoint that I presented in this group meeting about this dead end. That dead end may be something that another student can take and run with and overcome the problems. Sometimes you really don't have time. You're like, well, this is interesting. We tried it a little bit, didn't seem to work, so we pulled back and went this way. Got my thesis, got my master's, but that little trail may bear some fruit for some other student. The control piece is to provide enough notes for the student to come in and know what the pain was, know what stopped you as a dead end, okay, and know what might work, even if you didn't try it, so that they can start with a good effort. Okay. And so control is not always about process controls. Now in industry it is. You know, great, you finished this project, now how are we going to make sure that we don't slip back into our bad habits and have imprecise data? So, you know, if you have people making temperature measurements all the time and they're used to choosing Jmax, and you give them this Excel sheet and they're like, I hate Excel, I'm not going to use it. We'll go back to use Jmax. And so their temperature measurements are inaccurate and imprecise. So the control part would be to figure out a way to make sure that they're trained on that Excel, that they understand why it's important, and that they use it. So that would be the control that you might implement in the industry.
I can honestly say that through this, it's made me realize that most of my problems the reason I can't solve my problems is because I have inaccurately identified my measures.
Yeah, yeah. Even if a link dies, okay? So you're doing a Gaussian calculation and it says link died, okay? You've got to define the pain. The link died is maybe the initial pain, but there's a pain deeper in there. You got to go investigate. That's the measure part. What are you measuring? Well, you're going to the output file and finding at the bottom, why did it die? Okay, it died because it died right away because you misidentified the multiplicity or something, you know, and it can't have a charged molecule as a singlet because there's an odd number of electrons, and you can't have a singlet with an odd number of electrons. So that link's going to die in 2 seconds. Okay, and so then you've identified the problem. The pain is that you messed up the singlet thing, but then the analysis is, okay, I've got an odd number of electrons, I need to put in a doublet, okay, or quartet, which is most likely a doublet, okay, and then you resubmit. And then the control part is make an entry in your notebook. Be sure to check the multiplicity and the charge and make sure they make sense, okay? That's the control piece, so that the other student that's reading through your notes sees this asterisk on the page and it says, make sure you check the multiplicity and the charge to make sure they make sense. So you're passing it on, that's the control piece. Okay. So even something simple like that, you can use this thinking to go through the problems. Your problems are probably going to be a little more difficult than that in Gaussian. You're going to have something that doesn't converge, the molecule's too floppy or whatever. But that's why we have those controls. How do you know you're even doing the calculation right? You've got to do the controls first and make sure that you can get the same answer plus or minus a few decimal places, you know, as what's in the literature. And then you can do the unknowns. Okay. So any questions about the process? Appreciate your comments on that. I really would like to see you use these words in approaching these problems. And so, you know, when I said that the temperature thing was going to be on the exam, now that we've kind of done it in class, you know, it probably won't be. But as far as, you know, given a problem, I'd like to see you exercise these muscles, you know, in writing. So I also have that in the rubric for this Gaussian project. Like the last 10 points or so is what creativity did you have to use to solve your problems? Describe one of your troubleshooting methods or events and how you got over that. When I say describe it, I mean say, okay, my process would not optimize. That was the pain, okay? How did you analyze that? How did you approach it? What was the measure? You know, it went 99 cycles and just died. So did you restart the calculation or did you change the structure in some way? How did you, you know, what did you implement? And then have you documented it? So you can use this language, and I'll be looking for this language, because if I just tell you, tell me how creative you were, what are you going to write down?
I'm very creative.
Yeah, I'm very creative. Exactly. I love this project. I was so creative, you know. I put a methyl group right here. You know. No, I'm asking you how you solve the problem using these terms. What was the issue? You define it. Okay. you know, were there numbers associated? What kind of measurement? Was it in the output file and so on? You know, how did you analyze and implement a solution? So I'm trying to give you a framework for talking about the problems that you solved. Okay. And there probably are better ones than DMAIC, but I give you this one because it's part of the Six Sigma program. So if you do ever end up in industry and you run across this, you'll be a step ahead of everybody, and that's always a good thing. You know, instead of being there saying, "Gee, I don't know what they're talking about," Six Sigma. You know,
Nobody wants to be a green belt.
yeah, that's true. But no, you guys are gonna have graduate degrees. You're gonna be the black belt candidates. Yeah. So I would have just probably gotten ill and left if they were telling me what a pie chart was. I'd probably be like, I'm not feeling so good. I need to go home. And then I go get some work done. But I'm not going to sit there and have somebody explain what a pie chart is. Okay. But the black belt training was amazing because maybe you've had statistics. At the university, statistics is like the theory of statistics. But in industry training, they skip past theory in like 5 minutes and they get into how to do it. And you learn how to do it. And I interrupted the instructor because he taught me how many samples to run. If you want to have this precision and you want to have, you know, this kind of uncertainty over your signal to noise, essentially, how many samples do you have to run? I never ever had anybody in my whole chemistry career tell me, is 3 titrations good enough? What about 5? Do I have to do 50? How many do I have to do? There's equations for that. And I learned them in this program. And when we learned them, I stood up and I said, hallelujah, thank you. I've always had this question. And everybody's like, what a geek, you know. But I was like, now I know how many samples I need to collect, how many runs I need to do to get a particular signal to noise. Okay. And it was fantastic. So, anyway.